Swayam Prabha. Digital India. Educated India.
So, welcome again to the new lecture of the course, Properties of Materials. Let us just briefly recap the contents of last lecture. So, in the last lecture we talked about solid solution strengthening. So, that this happens when you form alloys which remain in single phase. So, basically let us say you have copper zinc, so it remains single phase, which means it remains single phase FCC when you add zinc to copper. So, you do not add too much of zinc, you just add a little bit of zinc, and this makes a substitutional solid solution because zinc and copper are similar in sizes. Substitutional solid solution. Similarly, you can have copper nickel. When you add nickel to copper, then also it makes a single phase FCC structure. It remains a solid solution throughout the whole composition range. On the other hand, we can also form things like FeC, which is iron carbon alloy, which is you can remain single phase BCC alloy up to very low percentage of carbon. Very low percentage of carbon, and here it is an interstitial solid solution. So, basically as long as the alloy remains in single phase by addition of a little bit of impurity, what you are doing is that basically this solute atom creates strain fields, and these strain fields cause strengthening, and this could be because of interaction of those strain fields with dislocations, or they are basically making the dislocation movement a little bit more harder. As a result, it leads to solid solution strengthening. So, basically in the early addition of impurity to an alloy, early stages of addition of an impurity to an alloy before a second phase of precipitate may form, what happens is solid solution strengthening. Now, when you add too much of impurity, what happens? When impurity added is beyond solid solubility limit, so when you add more impurity, what happens is that it leads to formation of second phase, and if this second phase is harder, or stronger, then it can cause precipitation strengthening. Okay. So, this is another way of strengthening that can happen. So, essentially in iron carbon alloys, let us say in iron carbon alloys, if you add, so if carbon content is percentage carbon is more than 0.008%, then what we form is, so we have alpha ferrite, which is solid solution of carbon in iron. So, carbon in iron up to 0.008%, but then any extra carbon will lead to formation of cementite, which is the second phase, which is a hard phase. Cementite. One of the famous examples is aluminum copper alloys. In this alloy, if you add more copper, so let us say when we have 4% copper, it leads to formation of precipitates which lead to increase in strength. So, basically what you will have is aluminum alpha, which has very little copper. So, you can say little copper. So, basically this is aluminum 4% copper alloy will have aluminum alpha with little copper plus Al2Cu precipitates which are harder, and they cause the strengthening, but there is a whole sequence that happens in this process that we will go. So, essentially what we are saying is that if you have a phase diagram like this, let us say this is the phase diagram, okay, and let me just talk about it. So, this is the phase diagram. So, let us say this is liquid phase, this is liquid plus alpha phase, this is alpha phase, and this is alpha plus beta phase. So, let us say you start from this composition, okay, we start from this composition C naught, this is temperature, this is percentage B, let us say this is AB alloy. Start from this point, this is 100% liquid. At this point you will have 100% liquid plus alpha, some percentage. At this point you will have 100% alpha, okay. So, basically this is 4% B in, so C naught percent of B in A, and it is a solid solution phase. Up to this point you have 100% alpha, but at this point you have alpha plus beta, and as you keep going down, you can see the solid solubility of B in A goes down. So, this shifts to, so basically the amount of B that can be kept in A lattice goes down. As a result, you can say the beta content increases as you cool down. Now, this formation of from one phase to, let us say, alpha to alpha plus beta is a time dependent process, time and temperature dependent process. So, what happens is that at this point you will have a single phase alpha alloy. So, this is all alpha. Somewhere around this point you will have essentially, and if you, now what will happen is that if you cool it fast, then again it remains alpha. So, you will have alpha, but this will be supersaturated alpha, because formation of beta requires some time, because the amount of B that is present in alpha requires some time to come out of alpha, because it is a diffusional process. So, since formation of beta phase requires movement of atoms, it is a time dependent process. As a result, when you quench it, what we have alpha, basically it is a supersaturated solid solution, it is a supersaturated solid solution. But if you leave it for some time, so if you leave it at certain temperature for certain time, then beta will slowly form in the matrix of alpha. So, now you will have alpha with solid solubility C alpha. So, here it will be alpha with C naught, but at room temperature it is a supersaturated solution. This is at temperature T1, and this is, let us say, room temperature, okay. This is at T1, this is at room temperature. So, you heat it at a temperature T2 which is slightly higher than room temperature, let us say this is T2. So, beta will precipitate through the process of nucleation and growth. Eventually beta will form in alpha matrix, and beta will have a composition corresponding to this end of the phase diagram. So, this is how it will happen. So, basically formation of precipitates is a time and temperature dependent process, and this is what we can control the way it happens to create hardening in aluminum copper alloys especially. So, basically there are 3 steps to form precipitates. So, steps are, you can say, one is solution treatment, which is basically holding at single phase region at high temperature for long enough time for all the impurity atoms to distribute themselves in the base matrix. Then you do quenching. So quenching is basically sudden cooling to room temperature, let us say, and then we do a treatment called as aging. Aging is basically slow, so basically heating to a temperature greater than room temperature, but lower than, let us say, this, if this was at T1, lower than T1 in two-phase region and holding. So essentially the plot is like this. If you say time and temperature, you first heat it to a temperature T1, let us say, and then you hold it and then you quench it. So this is solution treatment, and then quenching, this is heating, okay, and then you heat it to slightly higher temperature. So this is at T1, this is at T2, hold it and then again cool it. So this is basically your, you can say, aging treatment. So this is basically, you can say, single phase high temperature region, and this is two phase low temperature region. And why you have to do this is because formation of beta may not be straightforward process, and then directly forming beta by slow cooling may not lead to enough strengthening. So there are a lot of these alloys in which you do this kind of treatment. So we have alloys which have such as aluminum copper alloys. You can have aluminum copper magnesium alloys, in which you form precipitates of basically CuAl2 precipitates. So basically CuAl2 precipitates are formed, or you can have Al2CuMg precipitates in these. You can have AlMgSi alloys which have Mg2Si precipitates. We can have aluminum zinc magnesium alloys which have MgZn2 precipitates. So these are all precipitates, okay, but this precipitate formation goes through a sequence of processes that we will see. Similarly, you can have aluminum lithium alloys such as Al3, Li, and so on and so forth. So one of the signature of these alloys is basically we take example of aluminum 4% copper alloys, okay. So what happens in this alloy is that, so again in this alloy, the, if you say temperature percentage copper, so the phase diagram is again, okay. So let us say this is alpha phase, this is alpha plus theta phase, and this theta is essentially CuAl2 precipitate, okay. It has a different structure, so different structure, different crystal structure to that of alpha. So alpha is basically FCC structure, this has different crystal structure, probably orthorhombic structure. So what we do is that you take an alloy from room temperature of 4% copper, okay. You heat it to this temperature, let us say high temperature here, somewhere here, okay, and then, so first is heat it and then you allow the solution treatment, then you come back to a lower temperature somewhere around here, and then you hold it and then you cool it again. So you go from A to B to C and then you come to D. So formation of theta precipitate goes through a series of steps. So what happens is that alpha, when you cool it from, let's say, T1, it becomes alpha to, at this point again, let's say at RT, it is alpha but supersaturated. Solid solution of copper and aluminum, and this is 4% copper in aluminum. Now what you do is that this alpha, you heat it to, let's say, 150 degrees centigrade, T2 is 150 degrees centigrade, and then you sort of hold it, and when you hold it, this alpha transforms to what we call as GP zones, then it transforms to what we call as theta prime, then it transforms to theta, and then it transforms to theta prime, and then to theta. Now, so this happens as a function of time dependent. Now this transformation is also related to what we call as hardness of alloy. As a function of time. So it has a base hardness, so initial hardness, and then it goes through a peak, it goes through another peak, and it goes through a situation like this. So when you form ZP, so this is initially this is what we call as solid solution hardening. So you have some copper that will form solid solution. When you add more copper to it, formation of GP zones. So this is where you form GP zones. So GP zone is the first phase. We will come to the reasons later on. The formation of GP zones increases the hardness significantly, and then when formation of theta double prime to theta prime happens, somewhere you have a maximization of hardness, and when final theta phase forms, the hardness drops down. So this process is very important, because if you do it at a temperature which is low enough so that theta doesn't form, you get stuck somewhere between theta prime and theta double prime, then you can maximize the hardness of aluminum alloys. These alloys are called as age hardenable alloys. Age hardenable means as you age them, as you keep it at certain time, for certain time at certain temperature, they become more and more hardened. And this is, so what is basically GP zone? Let's say now what GP zone is. So you have alpha, which is alpha SS, let's say aluminum with 4% copper, supersaturated. Saturated. Now if you hold it at a temperature, let's say 150 degrees centigrade, then this forms what we call as GP zones. What is GP zone basically? GP zones are nothing but, so this quenched alloy has 4% copper, it has large supersaturation of copper, equilibrium phase diagram says that alpha will have 0.1% copper, and then you will have 7% of CuAl2, and this will be 93%. So while at room temperature alpha can have only 0.1% copper remaining going to form CuAl2 precipitate, we are having an alloy with 4%. So this copper is waiting to come out, but we have to provide it right condition. So as a result, what happens is that amount of copper that is present is about 40 times, 50 times higher. So there is a large driving force for precipitation. So driving force for precipitation, and this leads to formation of GP zones, which happens via a process called as nucleation. Okay, nucleation of second phase, and this nucleation of second phase happens first via formation of GP zones. So what will happen is that you have this alpha, and you will have these GP zones forming at various places. So this is at time, let's say T1, this is at T is equal to 0, let's say. So these are GP zones. GP zone is nothing but called as Guinier-Preston zone. So it says Guinier-Preston zones. This is called after Guinier and Preston because they were the first to image it or to visualize it. So one cannot directly produce a CuAl2 precipitate. So what happens is that, let's say you have this aluminum matrix, okay. In this aluminum matrix we put atoms of aluminum. So and the copper atoms were randomly distributed, so it was difficult to separate between the two atoms. So you can say so at T is equal to 0, it was aluminum 4% copper with copper randomly distributed. So you cannot make out which one is copper and which one is aluminum. Now at T is equal to T1, when GP zones form, basically what happens is that GP zones start forming in the form of, let's say, these middle ones are basically copper ones. So some of the copper ones are moved out, and as a result it sort of leads to distortion of the lattice. So the distortion of the lattice causes the lattice to bend around, so you can have some bending. So this atom may move to, let's say, this position, this atom may move to this position, so there is a slightward shift, let's say. Okay, and the new lattice may be like this. So there is a bit of distortion of the lattice. So this is basically a distortion of lattice aluminum lattice after formation of copper clusters. So what you have is this thing called as copper clusters. So these are nothing but you can say they become red, blue again. So you can say these are copper clusters, okay, and these clusters are called as, basically you can say, the GP zones. GP zones. So they don't break bonds. So you can see there is a still atom to atom correspondence. So they make an interface which is coherent interface. With some strain. Coherent means they need to, they still have atom to atom correspondence, which means you have atom to atom correspondence between aluminum and copper zones. Let me just wipe it a little bit. But since aluminum and copper have different lattice parameters, as a result, or different atomic sizes, they lead to some sort of strain. So there is a strain at the interface which leads to formation of these coherent zones. So as a result, this coherency strain basically obstructs dislocations. As a result, you have some strengthening. So this is, you can say, the first. So after solid solution strengthening, this is the first stage of strengthening, first stage of precipitation strengthening, okay, first stage of precipitation strengthening. So these also can be explained in the forms of, so if you have, they generally, precipitates are disc shaped, so these precipitates are disc shaped, let us say. So you can see these are disc shaped, very thin disc, of, let us say, thickness, the width of the order of about 10 nanometer, and this will be maybe about a few nanometer, very thin discs. So, within the microstructure you may see them. So, if you look at the microstructure, you may have these alpha grain boundaries. So, these are all alpha, and within this alpha you may have these thin sort of GP zones. So, these are very thin discs. So, they lead to some sort of hardening, and as they keep growing, and they generally grow in only one direction. So, stage 2 of growth will lead to formation of GP zones to what we call as theta double prime precipitate. So, because what happens is that as they grow, the strain energy also increases, and this sort of this limits the growth. So, as a result, so these discs become little thicker with time. So, something like this they are growing. So, eventually, because there is a driving force for the growth to occur, because more and more copper wants to come out. So, as a result, there is a growth. So, but you form what we call as theta prime, which is not yet CuAl2, but reaching somewhere there. So, let us say you have so basically let us say you have this aluminum and this another layer of aluminum, let us say, just drawing a schematic somewhere. So, let us say we have aluminum atoms like this, and in between we are forming these zones of copper layers, and let us say these copper atoms are and then on top we have these aluminum again. So, this is basically we can say alpha and or aluminum layer, this is copper, copper, copper. So, this still forms coherent interface with atomic contact, but with more distortion of at the interface because of strain due to higher strain. So, essentially it is going to look like if you have let us say you have a structure like this, in between we have a precipitate. So, precipitate has a lattice parameter which is similar to this, but your lattice has a parameter which is slightly different. So, lattice has, let us say, so it will have maybe one edge dislocation somewhere, and this is basically much smaller in size, let us say, as compared to the previous one. So, this is let us say the distorted region. So, this is basically you can say distorted region. So, this would be your, if you can draw the lattice completely, this would be your aluminum, that is alpha, this would be theta double prime. So, it is pretty much coherent, fully coherent, and so lattice parameter of aluminum is 0.404 nanometer, and for theta double prime the lattice parameter is 0.384 sorry, nanometer, not millimeter, and they are quite close. So, as a result they still maintain a coherent or sort of semi coherent strain interface. So, this again causes strengthening due to interfacial strain. The third stage is basically, you can say, third stage is where we have theta double prime changes to theta prime. So, when it changes to theta prime, which is basically some more copper is precipitated out, it is not yet CuAl2, but what it forms is a sort of semi-coherent, between coherent and semi-coherent interface. So, the discs have grown. So, the discs will be of the order of 1 micron, and the distance between these discs will also be of the order of 1 micron. So, these are bigger discs, you can say. So, if you now put this is in, so this is the precipitate, this is alpha, this is theta prime. So, interface will still be strained interface. So, this is a strained interface. So, this is again strained interface leading to hardening. Now, the fourth stage will be formation of, so this theta prime will convert to theta, that is CuAl2. So, what will happen is that in that case, so let us say this is my aluminum matrix, okay. So, this is alpha matrix. In this now I create phase which is like this, which has a lattice parameter something like this. So, you can see that this interface now, this interface becomes, so forget about what the blue ones inside, but this interface is incoherent because lack of atom to atom contact, and this basically happens because of necessity to relieve the strain, because as you keep growing GP zones into theta prime to theta double prime to theta prime, the interfacial strain increases, strain increases. So, as a result, so all surface energy decreases, but interfacial strain increases. So, to decrease that interfacial strains, you will have to then nucleate more and more dislocations. So, as a result, you will lose this interfacial contact or atom to atom contact altogether, and what you form is an incoherent interface with lot of many dislocations, and that is where you will lose hardening. So, that is why now this process is a temperature dependent process. So, when you do age hardening of aluminum alloy, so this is temperature versus time. So, you do it at such a temperature so that this is achieved after a very long time. So, let us say a few hundred hours. So, about 150-200 degree centigrade, and this is where your theta double prime to theta prime transition occurs. This is ZP zones, and then you stop here. So, you stop heat treatment and then quench. So, you quench at this point. So, you go to peak hardness. So, this is peak hardness, okay. Quench at that point, you do not want to go to theta regime. So, when you quench at that point, you go to room temperature. So, at room temperature you will start with, so now if you look at room temperature, you will start at, let us say this is H peak hardness, and this hardness remains constant because theta prime does not form easily at room temperature. So, theta will not form in normal duration of life of alloy. So, alloy remains hard because the kinetics of precipitates formation is very small. So, these basically precipitates form, formation of these precipitates leads to hardening, So basically we have said that theta double prime, GP zone, theta double prime and theta prime lead to hardening. Now how does this occur? There are two mechanisms through which hardening occurs. One is the precipitate shearing, and second is dislocation bowing. So in the precipitate shearing, what happens is that when you have a dislocation, and let us say this is dislocation line, you have a slip plane. So this is dislocation, and you have a precipitate, let us say here, this is a precipitate, and you apply stress to it, it comes to a situation where precipitate gets sheared in such a fashion as the dislocation passes through it. This happens when the precipitates are very small. When the precipitates are very small, they have a continuous slip plane with the matrix. As a result, dislocation can always find a slip plane through the precipitate and passes. So this happens when precipitates are very small, and this stress increases as r to the power half. So as size increases, the stress required for shearing increases. Second phenomena is at the same time when these precipitates start growing, then second thing happens is when these precipitates become bigger with larger separation between them, let us say L, then the dislocation line, when it approaches them and as it leaves them, these act as pinning centers. So these act as pinning centers. So basically then the dislocation, when it goes past them, it leaves these loops of dislocations around. So basically this leads to dislocation generation, which will again lead to strengthening. So as a result, there is a curve which one can draw for hardness. You have solid solution strengthening to begin with, and then you have this GP zone, then you have theta double prime, and so on and so forth. So in the beginning what happens is that, so this earlier stage is essentially solid solution strengthening. So this is, let us say, hardness H, and this is time at, let us say, 150 degree centigrade. And then initially you have formation of GP zones. So what we have is the hardness, which goes as the cutting mechanism takes place in this case, and so in this case what we will have is basically the dislocation precipitate cutting mechanism will dominate, and then here you will have Orovon mechanism. So this is also called as Orovon mechanism, okay, of dislocation bowing, and somewhere between them, when you have a critical size where the stress is maximized, you will have hardness like this. So this is maximum stress point. So there is a critical size below which precipitates are sheared because the stress required for shearing is lower, and after that the stress required for bowing is lower because precipitates have grown in size, their separation is increased. As a result, the stress required to bow is lower as compared to shear. So as a result, there is a critical stress. So when you look at the shear stress variation, so sigma as a function of precipitate radius. So this is the, let us say, shearing part. So this curve is basically, we can say, is this is bypassing curve, and this is shearing. So in this case the precipitate is going to be sheared, and here the dislocation is going to be, precipitate is going to be, so you will have these kind of precipitates. So when the size becomes increased, size becomes more, then the separation also increases as a result, because tau is equal to Gv over L, 2 Gb over L. So, as L increases, the tau decreases, hence it can bow easily. At lower, when they are very close to each other, then this stress is very high, but the stress required for shearing is lower. So, there is a critical size at which you achieve a maximum stress that is required, that is R critical. So, this is the size that we aim for achieving peak hardness, and this is a function of time and temperature. So, this is what happens in precipitation hardening. Basically, formation of hard precipitates in aluminum alloys goes through a sequence of nucleation and growth mechanisms. So, first, let us say in aluminum alloy, the copper clusters form what we call as GP zones, which have a coherent interface with the matrix, and they lead to certain strain at the interface. As these, because more and more copper wants to come out of aluminum, as you hold the alloy for longer time, these GP zones grow into theta double prime and theta prime precipitates, which are also coherent or semi-coherent with the matrix. They again contain a lot of interfacial strain. As a result, they again cause more strengthening, and the strengthening is because of balance between shearing and bypassing, and the peak hardness is achieved when you have this balance exact, when you are at critical size, when shearing and bypassing are balanced against each other, giving rise to maximum strengthening. And then as theta prime convert to theta, they become really very large, and then precipitates start, then the dislocations start bowing around them. As a result, the strengthening is lost. So, so these age hardenable alloys or precipitation strengthenable alloys are those alloys in which you want to form the precipitates of optimum size, so that you achieve maximum strengthening, and this happens after solid solution strengthening is already happened. So, initially you can see there is a drop in the strength because the copper comes out. So, as a result, I think earlier I increased in the earlier plot. So, this would be actually like this, yeah, this is not right, it should be slight decrease. So, because of slight decrease, because copper comes out of alpha. So, this is what basically precipitation strengthening is. Now, what we have covered up to this point is all the strengthening mechanisms, which means strain hardening, which is because of deformation, then grain size hardening, which is because of creation of more and more grain boundaries, that is by making the grain size smaller, which leads to obstacle to dislocation motion. Third is solid solution strengthening, which is by putting some impurities, but they remain in solid solution and they create strain fields which lead to destruction, dislocation, obstruction, and then formation of precipitates, fine precipitates of size that is optimum, which leads to maximum strengthening, and this leads to really hard alloys, especially in case of, let us say, aluminum copper alloys. You get very high level of strengthening. You can have strengths of the order of, the shear stress that you may achieve is about 400 megapascal. So, in fact, sigma could be as high as 400 MPa in these alloys, and corresponding the hardness can also be very high. So, this is where we will stop now. So, we have covered the mechanical properties aspect of materials, looking at elastic properties, the plastic properties, and finally the strengthening mechanism. From the next lecture onwards, we will start the electrical properties of materials, the basic introduction to especially metals and semiconductors. Thank you very much.